Welcome back to the Neuro Symbolic Channel. I'm Paulo Shakarian, and today we are going to talk about a new paper called Probabilistic Foundations for Metacognition by Hybrid AI. So this is joint work with my colleagues Jerry Samari, who many of you have seen on the channel, as well as Nate Bastian out of West Point, who's also a DARPA program manager. So let's first talk a little bit about the brand of metacognitive AI that we're engaging here. So we want to characterize model failure. And as I've mentioned many times, if you go out on the street and you see someone who maybe looks like me, your immediate reaction is, oh, that's Paulo. And then you might think, well, no, that can't possibly be Paulo. Paulo is in Arizona. And right away, what you've done is you've done a metacognitive process. You've used some additional information, what we would call a metacognitive condition in this work, to correct your perceptual information. And so the way we go about doing this in this line of work called error detection and correction rules is we first learn these detection rules. And if the rule fires, that means that there was likely an error. And we have learned these rules in different ways, such as optimizing an increase in precision while bounding a decrease in recall. We've also looked to learn these rules in a way that maximizes the F1 of the ability to predict an error. And you could think of, after applying these rules, you're essentially erasing the results of the machine learning model. And then the next step is to do some kind of correction. So maybe we have another set of rules to change the labels to something else, or we use some other approach, and we've done some work with logic tensor networks, for example. And we have some ongoing stuff with language models. So let's talk about a couple of the prior papers, because what we did is we had some results here that have been largely empirical. And then in the work that we're talking about today on probabilistic foundations, we re-examine the assumptions and how we develop these algorithms from a probabilistic standpoint, and drawing new conclusions about both explaining some of the results that we've gotten empirically, as well as identifying some potential limitations. And so in our logical framework, we learn rules of this format, and the paper I'm showing here was presented at CIKM in 2024. And you have some set DCY of these metacognitive conditions. And this rule is saying if any of those conditions are true for sample X, and the model assigns label Y to sample X, then it's likely an error. So we want to learn rules of this form. And the key is to learn this set DCY. And so in this work, we used submodular ratio maximization, some ideas from combinatorial optimization. And we came up with an algorithm that maximized the F1 of the error class. So if you think of, you have a bunch of samples and treating it as a binary classification problem on if the model is getting the sample classified correctly or not, you can use this algorithm to maximize the F1 for the error class in that setup. Now, this is a multi-class classification problem, so we can look at it for different potential labels. And also in the problem that we examined, we looked at multiple resolutions of labels. So it was a hierarchical classification problem. Our key insight in this work was using the hierarchy. We could use one layer of the hierarchy as the conditions, and the other is this assignment of the labels. So what that results in is you have these metacognitive rules that actually have a meaning beyond metacognition. We're learning about classes that don't belong together, because if they're put together by the algorithm, there is likely an error. And so we were able to show that we were able to recover the ground truth of the constraints by examining these rules. And then we use these error detection rules with logic tensor networks, basically integrating them in the loss function. And we showed that we could improve performance, as you see here in this example with the open image data set. Then later in 2024, we had another paper, an ICDM workshop paper on metal spike price spike prediction. And here the idea was, we have a problem where we're trying to predict based on a time series data, we're trying to predict if the next time period, the price of the metal is going to spike, is going to be a certain number of standard deviations above the moving average. And so to solve this problem from a machine learning standpoint, once you define the spikes in this way, it's a classification problem where you have sort of a many to one. You have many items in your input, so a bunch of price information, a vector of prices over a window of time, and you're just trying to produce a result that's either yes, there is a spike, or no, there is not. And machine learning gives us a lot of rich methods to do this, such as recurrent neural network, attention. You can even do this with convolutional neural network. And in doing this, we could train a bunch of models and get varying results. And so we would just use the results of one model as the condition. So what you see here, the condition, if CNN number one predicts a price spike and our base model does not predict a price spike on sample omega. Now, since this is a binary problem, unlike before, we can not only say there's an error, we can say, hey, we're going to go ahead and predict a spike. And so in doing this, we're able to learn rules on errors for the non-spike class. So actually the class that we don't care about, because we can relabel that. So in other words, we want to bump up the recall of our ability to predict spikes to do a better job on this problem and do this as a sort of a smart ensemble. Now you might think, well, why not just vote? Well, here's the thing. If you're just training models in kind of an arbitrary way, you don't know which ones correlate and which ones do not. So majority voting can easily reach a degenerate case because you could have a bunch of recurrent neural networks that are all very similar to each other, and they're just going to agree all the time. So our empirical findings showed that we got significant performance improvement with this approach. And we did this for several different metals. So, and in a third paper that right now is under review, but on archive, again, we have the same kind of setup with the rules. So we have our error detection rules, just like with the perception paper. But now here we also have correction rules. So once it's erased, it allows for a relabeling. Now here, we were able to have some theoretical results based on support and confidence of the rules and provide this theoretical guarantee and recall. Now notice we don't hit it, we're doing a little better, and this is likely because of the correction rules. And the other idea is that as we erase labels, we want this precision to zoom up as much as possible so that the F1 outpaces the reduction in recall. And using this method, just looking at detection only, you see here, we're getting really great results on the ability to detect errors. Then when we look at correction, we do get improvement. Now, this is with the same data set. It's not as drastic as what we would expect, being at how good we are predicting errors. And this is one of the things that we explore in the theoretical results that I'll show you soon. The other interesting thing, though, is when we have, one of the classes not present in the training data, EDCR is able to metacognitively reason about the existence of samples that don't fit in any of the classes. And what we see here is even with no training data, EDCR is able to improve accuracy significantly by identifying these particular samples. And then as you feed it a little bit of extra samples used in rule learning, so note here, there is no retraining to the baseline model, we get performance that starts to approach just as if you would have trained the model with all the data. So anyway, that concludes the prior work. So let's talk about the preliminaries for this. So we have a simple example in the paper. So we have a multi-label classification problem where we have countries like US and Japan, and we also have different types of car manufacturers. And for a given sample, we want to give it one automobile manufacturer and a country of origin of the car. And so we want to learn rules like this. And so here we see that, for example, if we have a prediction that the car class is, or the model car is predicting Toyota, and then we also have a prediction that it's US, then we say that, hey, this is likely an error. And then maybe we have a correction rule that, hey, every time it says it's both a Toyota and a US car, the right label should be a Dodge. And in our notation, F is just the model. So we have F car. Omega is the sample, the argument, and that's also the argument that appears in the logic. And then we have this return set of labels. Now, so we start defining our probabilistic formulation in terms of conditional probabilities. And we'll use the notation, we'll say A or alpha is in set GT, meaning it's in the ground truth, conditioned on alpha being returned by the model. So we treat the model notation here as a set of elements. Okay, so it's a set of labels returned, just to keep the notation kind of concise. So precision and recall are defined in a very direct fashion. This makes sense. The probability of alpha being the ground truth, conditioned on it being returned by the model, and recall is the probability of alpha returned by the model, conditioned on it being the ground truth. Now, these probabilities change when the condition is present. So we want to consider the case when the condition is not included to judge, the performance improvement. Now, note that we only consider a single condition, but in the work, a condition you could think of as a disjunction of conjunction of, component conditions. So that just keeps it a little bit cleaner when the conditions, which can be a formula of things, is true. So if that condition is not present, then we're going to allow the label to be assigned. So we're now computing precision with a subset of labels, and recall. We are considering recall of all samples where the condition is not true for that given class. So we're looking at the precision and recall here. Okay, so where do conditions come from? Well, we talked about this a little bit in the related work. With the vision work, we looked at complementary classes. With the ICDM work, we looked at a different model. And with the preprint from arXiv, we look at domain knowledge, and we also look at binary versions of the classifier. And we have two definitions in the new work that we define. We say a condition is error detecting if the probability when the conditioned on when C is present, if that is less than it is otherwise, then we say it's error detecting. Now note we add this additional random variable D, and we're saying this is for some distribution D, and we're saying a metacognitive condition is distribution invariant with respect to the model and the class and some set of distributions. If for every distribution in the set, it's error detecting. So you could think of something like, hey, if you saw me on the street and it really wasn't me, you know the condition on Paulo being in Arizona, whether that person in another state is Paulo or not. That would be invariant no matter how you train the model. So from here, we get necessary and sufficient conditions we were able to derive in the paper. And this deals with the kind of results that we've seen in the in the trajectory classification work. So the theorem here is we look at the change in precision. So the change in precision, which is this is the precision when condition C is present minus the initial precision, it's equal to K, which we define below, multiplied by this probability minus 1 minus the initial precision. And so essentially what you see here is that this increase in precision really hinges on two quantities. It's the probability that A is not in the ground truth, given, or alpha is not in the ground truth, given that alpha was assigned by the model and C is, condition C is present. So this we could think of as the rule confidence, essentially. This is the fraction of the time that the rule is giving the right answer. And this other quantity here in the numerator, because you have 1 minus that in the denominator. So in the numerator, you have the probability of the condition being true given alpha is returned by the model. So this is proportional to the support of the rule. So this theorem validates the empirical findings, but what's interesting is we were able to prove this without any underlying independence assumptions. And this is what gives rise to the necessary and sufficient condition for precision improvement. Essentially the confidence of the rule has to be greater than 1 minus the initial precision. And so this also gives rise to necessary and sufficient conditions for being error detecting. So next is with reclassification. So, here what we see is we look at the task for the binary classification problem, where if we detect an error, we're just reassigning it, and these results are quite good. This is from the ICDM paper. So we're getting big improvements in all metrics, okay? F1 is going up, about 6% here, okay? Or 10% when you look at the ratio. It goes up by 6 points. Meanwhile, when we have a multi-class problem, we see with the trajectory problem, we are getting precision improvement, but the recall improvement is about as much as the precision is improving, and your F1 is kind of flatlining here. And this is even after the correction step. So we were wondering, why does this happen? Well, this leads to the limits of reclassification. So what we have here in the statement, if the probability that beta is in the ground truth, given alpha is returned by the model and the condition C is true. So basically we're saying, hey, how likely it is you belong to class beta, given it was initially classified as alpha and C was true. If that is less than the precision associated with class beta, then what you got is the probability of beta being in the ground truth, given beta being returned by the model, is going to be larger than beta in the ground truth conditioned on beta being returned by the model or alpha being returned by the model and along with C being present. So in other words, you can get a reduction in the precision for class beta due to this reclassification step. If you check the probability of beta being true for alpha and the condition being true, if that's lower than the initial precision of beta, then this is the precision of beta after you reassign the labels identified by the condition. That is also going to be less than your initial precision. So you're going to have a loss in precision for class beta with the reclassification. And so think of it this way. A well-trained model assigns class I. It's the most probable class by training. But the probability of I is lower than the average precision for all predictions of that class. So we could clearly find this through error detection. However, the next most probable class J, or beta in the statement of the theorem, it's still low. So picking class J would cause your overall metrics to be lower still. And the reason for this is both the models and conditions cannot reassign those samples to new labels to improve performance. By both the conditions and the model, those samples are all identical. And we'll show a little graphic on this next. So let's say we have overall precision of 0.9 for class 1 and 0.8 for class 2 and 0.85 for class 3. Let's say we have a subpopulation of 10 samples. So all of them are identical by the features or how they look to the neural model, as well as the conditions. And let's say 60% are in class 1. Now, what you got here, though, is notice that your performance on class 1 is lower than your overall class 1 precision. So this would come up as being likely to be an error because these are all under the same metacognitive condition. But if I reassign class 2, because these are all identical, I only am doing about 20% precision on class 2 or class 3 for that matter. And so if I go to class 2 or class 3, then I'm going to lower the overall precision for those classes, potentially by even more than I would for class 1 because I'm going to have way more false positives. So this is the limits of reclassification. This is why with the trajectory classification, we saw some really excellent performance for error detection. And in the case where we're reassigning stuff with the rules, we're only getting this like 1% improvement. And I believe this is the reason for that. So we have a corollary from this. So we can get a test for a condition to be error detecting. And so we say if C is error detecting, then the probability of C being true given alpha was predicted is going to be less than or equal to the probability of the condition given that alpha is not in the ground truth and alpha is predicted. And so not in the paper, but this is equivalent to the following statement when you look at when you change the condition on the right-hand side of the inequality, it causes the symbol to flip. So here we have the probability of the condition being true. And this is the condition being true given that the model was incorrect. So what this is telling us is this probability of the condition being true given the model being incorrect, it could give us direct insight into the effectiveness of error detection. And we would expect for a well-trained model that we could compute this probability with a frequentist approach with only a small number of samples, because it's not, it shouldn't be very many samples where the model's getting it wrong, because the model should be well trained. The same quantity is also an upper bound of support, so we can also get some insight on the ability to improve precision as well. So what are the implications? Well, the empirical, our empirical findings showed learned conditions can specify constraints on class relationships, and we're actually able to recover those constraints. So does this suggest we can algorithmically identify distribution invariance? That would be kind of the big thing, because if you can identify distributional invariant conditions in a consistent manner, you could really add on these rules and generalize machine learning models beyond their training distribution a lot better. We saw particularly with the metal price spike prediction, that we could use error detection correction rules to ensemble the model, but this assumed that we had one base model. So can we do this without knowing which model should be the base model? And we would get different results depending on what we use as a base. And the reason for this is we would start with a base and kind of adjust off of that. Also, with the trajectory stuff, we saw that this can enable few-shot learning. What are the limits in terms of data efficiency? We, looked at, for example, that last result where we had the test. That gave us some insight into how we can get a clue as to, hey, is this condition working or not, without having to do a lot of calculations. At the same time, can we use this to, from a standpoint of data efficiency, did we have enough samples to sufficiently do learning for a rule to identify a new class or identify errors? So here are some references of the papers I mentioned, and really want to be thankful to my sponsors from DARPA and Army Research Office for their support in this work. So that's it for this video. Thanks again for tuning in. Don't forget to like and subscribe.